Hello, and welcome to Austintronics. I've made past videos on this channel showing the progress on a RoboDog I'm making, so if you want to follow along with me on this journey, feel free to check those out. In this video, I'll be showing you my very own embedded operating system that I created from scratch for the Zinc chip on the Zybo board. But no, I'm not just going to show you my OS. I'm going to teach you how to build your own. This includes all the components in the software stack from the moment you turn on the system all the way to when a user has control over that system. By the end of this video, you'll have a good foundation of the different software components required to get your own custom operating system up and running and how to put a variety of software packages on the system for the user to interact with. You'll be able to mix and match what software components you want and learn how to build all these components from the source code itself to give you a ton of flexibility. This seems pretty intense, but don't worry, I'll be going step by step and I don't assume for you to have any prior experience in OS design. However, it'll probably help if you have some prior experience with embedded systems, or if you've used a terminal on a Linux OS before. But even if you haven't, I still think you'll be able to grasp most of the concepts in this video. So, why should you care about making an OS? There's already several great pre-made OSs out there to choose from, right? Remember, we're talking about embedded operating systems here, not desktop operating systems. Embedded hardware platforms are like unique little butterflies. There's a ton of them out there, and they almost all try to accomplish some specific goal when it comes to your bigger system. You'll even have some folks go through the whole process of making their own custom embedded hardware because it integrates into their system better. Like in the case of, a RoboDog? Yes, my eventual goal is to design my own embedded hardware for RoboDog, and in doing so, along with creating my own OS, I'll have optimal hardware and software that's configured and optimized for my exact system. But before I go out and design my own embedded hardware, I'm prototyping on an existing embedded platform first, which is the Zybo Z7-20 board from Digilent. But making your own hardware may not be the only reason why you'd want to make your own OS. Consider this. You want to make your overall system very secure and reduce attack vectors for bad actors to exploit. The less baggage you have running on your OS, the harder it is for a hacker to do something malicious. A pre-made embedded OS may not have those goals in mind, or may not even be aware that your specific hardware has a special chip on it for cryptographic functionality that you want to use. The last thing you'll want to end up doing is trying to hack together some Frankenstein OS to meet your exact needs. Or what if one of several background processes that are running on your pre-made OS crashes and causes your entire system to go down? And what if that process wasn't even needed in your overall system to function properly in the first place? Or maybe you just want a better understanding of how all the different software components in an OS interact with each other. Whatever your reason may be, having maximum control over what goes on in your embedded system is something that I don't see a lot of people addressing. So I'll be showing you how to have much more control over your system as I build up my own OS for RoboDog. And just so you all know, what I'll be showing you isn't unique to just the Zybo board platform. In fact, if you want to make your own custom OS on other embedded system platforms, this video should be a good starting point on how to do that. I'll first start with a general overview of what components are needed so an OS can properly function. Then I'll dive into the specifics of what exact OS components are needed for the Zybo platform. Then I'll move on to showing you how to install some tools you'll need to help generate some of these components. Then I'll walk you through the process of actually generating all of those OS components. Once all of the OS components are generated, I'll show you how to partition and format them onto an SD card so that the Zinc chip will know how to retrieve them. And of course, I'll show you how I interface into the board to show off our custom OS booting in all its glory. I'll also show you how to update and maintain your own software package repositories so that you can install software packages on your embedded platform over Ethernet during runtime. This will help speed up your development so you don't have to reflash the SD card every single time you want a new software package. Then finally, I'll wrap everything up by showing you more advanced configurations you can make to your OS components if you want additional modifications, as well as how to download and interact with my RoboDog repo on GitHub. So what's actually needed to get a processor up and running with an operating system? Well, you generally need a bootloader, a kernel, a DTB or a device tree blob, and a root file system. Let's first start with the bootloader. Without getting into the gory details, the bootloader is a program that gets handed over to the CPU as soon as you turn on the board. This bootloader can either come from memory located on the board, or can even be transferred over some external interface like USB or Ethernet. It's responsible for helping initialize some of the necessary hardware components on the board for the rest of the OS components to run. The bootloader is often referred to as a bare metal program, meaning that there are no other programs running underneath it to help support its operation on the platform. It is, in a sense, the program that's closest to the bare metal of the chip that interacts directly with the hardware. In contrast, applications a programmer would write on an OS are not bare metal because they don't need to have the know-how to interface with the hardware directly. One of the more common bootloaders is called U-Boot. U-Boot is a pretty generic bootloader that works on many embedded systems. We'll be using this for our platform as well. Once the bootloader configures the hardware, the bootloader fetches the kernel and passes control over to it. So at this point, the only thing running directly on top of the hardware is the kernel, which makes it a bare metal program. However, unlike the bootloader, the kernel is a lot more sophisticated. It contains all the drivers that you need to talk to most, if not all, of the hardware on the system. In my case, I'll be utilizing the Linux kernel, which is a super common kernel across the embedded industry, but there are other options that you can go with if you wanted. Now you might think that with so many different embedded systems out there, how is it possible for a generic bootloader like U-Boot or the Linux kernel to know how to set up and configure the hardware for all of them? That's where the device tree blob comes in. The DTB is a configuration file that configures the bootloader and kernel for the specific embedded system that these bare metal programs are running on. So essentially, you would have a different DTB file per embedded system you wanted to target. Lastly, there's the root file system, or RootFS. Generally, when you think of a Linux OS, people's minds go straight to Ubuntu, Fedora, CentOS, Raspbian, or a handful of other OS distros. But what's actually giving you that flavor of Linux OS stems from what's in the root file system. This makes sense because the root file system is what's closest to the user. They are directly interacting with it after all. The interactive shell you're using, all the commands you use, the type of file system you're using, and the package management system you use, they all derive what dependencies you're placing in your root file system. So far, we've covered the different elements that are needed to get a generic embedded system up and running, which are the bootloader, a kernel, a DTB, and a root file system. But let me get a little bit more specific with the Zinc chip that's on the Zybo board we're working with. The Zybo Z7-20 board was built around the Xilinx Zinc 7000 family, which contains both an RTX 7 FPGA and an ARM Cortex A9 processor on a single chip called the Zinc 7020. It is common in industry to call a chip with an entire system like this a system on chip. However, Xilinx calls this chip their all-programmable system on chip, as a testament to how much more customizable this chip is compared to other system on chips on the market. Here's the system architecture of the Zinc 7020 system on chip that's on the Zybo board. This diagram is from the Xilinx Vivado tool and is what my current configuration is for booting up the OS, but don't worry if you don't know what the Xilinx Vivado tool is yet. We'll get there in a second. If this is your first time seeing something like this, it can be a bit overwhelming, so let's just break down some of the blocks that are involved with this system diagram. The Zinc is split up into two regions. This is the PS, or processing system, and this is the PL, or programmable logic, which is essentially the FPGA. In case you're confused on what an FPGA is, I covered this in the first RoboDog video if you're curious and want to check it out. The PS is what has the ARM Cortex A9 CPUs, along with everything necessary to support the software that will run on top of them. You can think of the PS as an area of the chip that has its digital logic fixed. You may be able to configure some components of the PS, like running software on the CPUs and configuring certain registers of different digital logic components in the PS, but as far as the digital logic is concerned, there's no changing it. Fixed digital logic to support a CPU is often referenced in industry as a hardcore since it can't change. However, unlike a hardcore on the Zinc and the PS, the PL is an area where you can freely create your own digital logic to expand the capabilities of the Zinc chip. If you wanted to, you can create an entirely separate CPU along with supporting components in the PL, just like in the PS, but because this is in the PL, you would have to call it a softcore instead, since you can freely modify its digital logic components. I'll place some digital logic in the PL region a little later in the video just to give you a feel for what it's like, but since we're primarily focusing on bringing up our own OS, the PS is where I'll mostly be focusing on in this video. Looking at the PS region a little closer, you have components to support caching between the two CPUs, as well as on-chip memory interconnect along with some static RAM, your global interrupt controller, a system watchdog timer and some triple timer counters, a memory interface controller to access the DDR3 RAM that's on the Zybo board, I/O peripherals, various flash memory interfaces, and several other components. All these components can be used at the discretion of the software that's running on the CPU, like the bootloader or kernel, and you have the DTB file, which helps the software set proper configurations for some of these hardware components. Let's go step by step here, starting from when you first turn on power to understand the flow of what the PS is doing and how it's loading the software. After the Zybo board is powered, CPU 0 will fetch and execute an internal piece of code from read-only memory called the BootROM. Although it's not shown in this diagram, the BootROM code is accessed via the on-chip memory interconnect. This is software that is hard-coded into the ROM memory during manufacturing, and it can only be read from and not written to. The BootROM, now executing on the CPU 0, will check the state of the mode pins located at JP5 on the Zybo board to determine where the CPU should fetch the rest of the code it needs to run. Since I have mine set to the SD card, the BootROM will fetch the first OS components to run from the SD card, which is the bootloader. And just as a side note, Digilent, the Zybo board manufacturer, routed the signals of the SD card slot to multiplex input-output pins 40 through 45 and pin 47. Because these are multiplexed pins, you can configure a variety of different peripherals to these specific MIO pins. But if we want the SD card slot to work as expected on the board, then we need to make sure that the SD0 peripheral controller in the Zinc chip is specifically connected to these pins so it can communicate with it. Here's the pinout configuration I'm using that's mapping the correct peripheral to the correct MIO pins for the Zybo board layout. I will go over how these are set later in the video, but if you want more information about which MIO pins should be connected to which peripheral to sync up on the Zybo board layout, you can refer to the Zybo reference manual on Digilent's website if you want to know more. I'll put a link in the description. So when the BootROM fetches the bootloader from the SD card, it places it in the 256 kilobyte memory of the internal static RAM, or SRAM, so one of the CPUs can execute the code later when the BootROM code is finished running. After the entire bootloader is transferred over to SRAM, the BootROM will hand off execution to it. However, because the Zinc is a little more complicated than your average system on chip, it is common practice to use two bootloaders for it. The first stage bootloader is called, First Stage Bootloader, or FSBL for short. Creative name, I know. It's a custom bootloader that Xilinx made for their products, so it's more or less tailor-fitted for the specific Zinc chip that you're working with. The second stage bootloader will be U-boot, similar to what was mentioned before. When the BootROM fetches the bootloader from the SD card, it really is only grabbing the first stage bootloader, not both bootloaders. Having two bootloaders like this gives the first stage bootloader the opportunity to configure some of the essential hardware needed during the booting process before passing control off to U-boot. This methodology is useful because U-boot or the kernel may not have all the know-how to configure hardware components specific to the Zinc chip. It's also worth mentioning that the first stage bootloader also configures the PL with your custom digital logic if a bitstream file is present. More on this later though. Next up is U-boot. U-boot is loaded into DDR3 memory since the first stage bootloader properly initialized that memory interface controller, and then execution is then handed off to U-boot. From here, everything is the same as the steps presented earlier in the video. U-boot runs, grabs the DTB config file to get some help on what it should configure and how it should configure it, then it fetches the Linux kernel and places it in DDR3. U-boot will pass control off to the Linux kernel, and the kernel will also configure a bunch of hardware with some help from the DTB config file. The hardware that both U-boot and the Linux kernel are configuring may be hardware that hasn't been configured yet, or hardware that has been configured but needs to be reconfigured so the software execution can operate more optimally. Finally, the kernel will grab some parts of the root file system from the SD card and place it into DDR3. Luckily though, the kernel doesn't need to grab the whole entire root file system since it's pretty big. It just needs enough to mount the file system so there's a known and established pathway from the CPUs, and also run the first process called init that proceeds to spawn a few more processes to provide a good user space for a user to interface with. The reason why you see parts of the root file system in DDR3 and cache is because data that is being read from the file system will often reside in those components because it needs to be quickly accessed the next time it's requested. Now let's rewind a little bit to when the first stage bootloader configured the PL with your digital logic. I said that if a bitstream file was present on the SD card, the first stage bootloader would load this into the PL. A bitstream is just a file that describes what digital logic you want in the PL. For my particular use case, it's convenient having the first stage bootloader load this for me, but it's also worth noting that you could have U-boot, the Linux kernel, or even a user space application like Python load the bitstream into the PL instead. You may want to do something like that if you want to have more control over when you write to the PL, or maybe you want to leverage some hardware in the PS region, but you want to wait until it's configured by one of the bootloaders or the kernel before you instantiate the bitstream on the PL. So hopefully by now you have a good idea of what OS components are involved and what the boot flow process looks like. To recap, we'll need an FPGA bitstream, which is optional in the booting process, but I'll be including one anyways, Xilinx first stage bootloader, U-boot, a U-boot environment text file, which we haven't talked about yet, but we will. This is also optional, but makes things more convenient when setting up your U-boot environment variables, the Linux kernel, the DTB file, and the root file system. All of these OS components will need to be on the micro SD card so that we can run our custom OS on the Zybo board. So now we know exactly what we need. I'll switch over to my Ubuntu desktop so we can start generating all these OS components. One of the first questions that you may be asking is if you need to use Ubuntu Linux for everything I'm about to show you. No, actually, you don't. It's possible to run Xilinx tools on Windows or other distributions of Linux. However, when we get to generating other OS components like the root file system, the tools we'll need to use will have dependencies associated with Linux. So if you're trying to build all of the OS components, you'll want to use a machine that's running some distribution of Linux. Just for reference, I'm running an Ubuntu 18.04.5 OS on an Intel Core i9 processor. This is running at about 3.5 GHz with 32 GB of RAM. This has about 12 cores with hyperthreading enabled, so it's really 24 threads concurrently. This is a bit overkill, and you don't need to have this powerful of a machine to build these OS components, but it does make compiling a lot quicker for some of them. For creating the FPGA bitstream for the PL and Xilinx's first stage bootloader, we need to download and install some software tools called Vivado and Vitis. Vivado helps you create the bitstream, and Vitis helps you create the first stage bootloader, or any other applications you'd like to run on the CPU on the PS side, whether that be bare metal or higher level application. Luckily, both of those software tools are free and can be installed by one software package on Xilinx's website. So let's do that now. The first thing you'll want to do is go to the Xilinx download page for Vivado, which I'll put a link in the description. If you scroll down a little, you'll see a couple of links for how you want to download and install the Xilinx tools. Since I'm on Linux, I'll choose the Linux self-extracting web installer. Xilinx will ask you for a login before you can download anything, so make sure that you create an account with them first, with the Create Account button below. I already created an account, so I'm just going to log in. Once all the information is filled out on this page, you can scroll down and click the Download button. Once the download is complete, navigate to the download directory and make the binary file that you just downloaded executable with the chmod +x command. Now you can execute the binary file. I'm getting this warning here because the OS I'm running, which is Ubuntu 18.04.5, is slightly an upgraded version of the 18.04.4 version Xilinx supports. But I've ran Vivado and Vitis on this machine before without any issues, so I should be fine here. After selecting Next, you'll need to put in your Xilinx login again, then select Next. Then you can just accept the defaults for both of these pages. Make sure to read the license agreements and terms of conditions before proceeding. After pressing the I agree checkbox for all of them, click Next. The Tools Xilinx path will be the location that the installer will download all the Xilinx tools to. You can change this if you'd like, but I'll be using the default. As you can see here, the disk space required for this install will be about 143 gigabytes. Press Next, then press Yes, and select Install. This whole install took me about 1 hour and 15 minutes. Now that we have Vivado and Vitis installed, let's create the FPGA bitstream for the PL. We can do this by opening up the Vivado tool and creating a Vivado project. Click Next, then enter in your Vivado project name. I'm naming this LED switch test because I'll only be creating some digital logic in the PL that connects some switches to lights, or LEDs, that are on the board. This is so that you can get a little more familiar with how development works in the PL. I'll be developing more advanced digital logic for the PL in later videos for the RoboDog. Then enter a project location. I'll be saving this under my RoboDog directory. This is also my Git repo that's linked to my GitHub, so everything I'll be doing here can be found and downloaded there. I'll put a link in the description. After entering your project name and location, press Next, and then accept the defaults here by pressing Next again. Here we are presented with different Xilinx chips that you can build your bitstreams for. However, it's better to select your particular board if you can, since Vivado will pre-configure a lot of settings that will be helpful for you when creating your Vivado project. I'm using the Zybo Z7-20, so we'll choose this option. If you don't see your board listed here, you can try clicking the Install Update Boards button to see if Xilinx Hub has the board you need. Different boards could be from Xilinx themselves or third-party vendors like Digilent or Avnet. Here are a couple boards as an example. If you still don't see your board here, don't worry. You can still manually place the required board files in your Vivado install directory, which will be under Tools, Xilinx, Data, Boards, Board Files, if you haven't changed the default directory during installation. You can usually get the board files from the same vendor that's providing your board. Once you've selected the board, select Next, and then Finish. Now that the project is initialized, let's load in the constraints file. The constraints file can be found on Digilent's GitHub. I'm going to save this file to the same directory as the project. Then I can add it to the project by right-clicking on Constraints, clicking Add Sources, clicking Next, clicking the plus sign, and selecting Add Files, then clicking on the constraints file that you just loaded, and pressing OK. Then Finish. The constraints file tells Vivado which pins should be connected to which highest level ports in the design, as well as other general information about the ports or specifics about timing in the design. If you don't know what any of that means, I'll be getting back to some of this in a second, but first, let's uncomment some of the ports that we'll be using. We'll be uncommenting the pins dedicated for the switches on the board, as well as the pins for the LEDs. Then make sure to save the file by pushing Ctrl-S or the Save to Disk icon. Now let's jump into making the block diagram by pressing Create Block Design in the Flow Navigator area. I'll keep the default name for the block design and press OK. After pressing OK, you'll be presented with your work area for creating your block design. I'll double-click the Diagram tab to enlarge the area. You can either hold down Control, then press I, or press the little plus icon in the center of the diagram to bring up the Search tab for the pre-created digital logic blocks known as IP cores. IP standing for intellectual property. So let's add in the Zinc Processing System IP core. This is actually a pretty unique IP core since most cores are instantiating that particular digital logic in the PL. However, this IP core is more of a configuration block for you to configure how the hardcore processor in the PS region will be configured. Most beginners will actually confuse this for creating some sort of soft-core processor in the PL, and that's just not the case here. You can run the block automation tool, and it will automatically make certain connections for you that it assumes you want, like connecting the processor to the DDR and to various fixed IOs. For establishing a communication path between the PS and your digital logic in the PL, we would normally use something called an AXI bus, abbreviated AXI. Since we're just connecting some LEDs to some switches, we don't need to make an AXI bus for this project, so we can remove these references to AXI located at these ports. We can remove it by double-clicking the IP core. This brings up the configuration panel for the system, which should look familiar to you. This is where you can configure various settings in your PS region. What we want to change is located in the PSPL configuration tab. Expand the AXI non-secure enablement, GP master AXI interface, and uncheck MAXI GP0 interface. Press OK. You'll see a few warnings pop up. It's okay to ignore them. Even Digilent has acknowledged these warnings and has provided documentation on why these warnings pop up on their website. I'll put a link in the description if you're curious. After pushing OK, you'll see that the IP core removed the AXI interface from the diagram. The next step is to add the logic for having the switches control the LEDs. Start by right-clicking the canvas, then select Create Port. The name of this port should be SW for switch, and it should be an input. Vectors are 3 to 0 because there are a total of 4 switches on the board. Then press OK. The reason why we would want to name the port SW was because that's what the name was in the constraints file. If we named them anything differently, Vivado wouldn't know what pin that port would be tied to, unless we updated the constraints file. Similar to the switches, we need to use the same name as the LEDs when we create the 4 LED ports. I'll do the same as before, but this time I'll name the port LED, make it an output, and have the vector of the signal be from 3 down to 0 since there are 4 LEDs that we specified in the constraints file. So now all we need to do is hover over the port until you see the pencil icon, then click and drag to the other port. And that's all there is to it. To make this diagram look a little nicer here, I'm just going to click the Regenerate Layout button. And then I'm going to click the Validate Design button to make sure there isn't anything wrong with the design I just created. Now that it says there are no errors, I'm going to save this project and generate the VHDL based on this block diagram. You can do this by going to the Sources tab, expanding Design Sources, then right-clicking the Design 1 block diagram file, and selecting the HDL wrapper. Press OK. After a few seconds, the VHDL will be created. You can see that the top file is now blue, representing HDL source code. If you click it, you'll see what the top-level VHDL file looks like. For those that don't know, VHDL is a programming language that's used for describing hardware. So what we're doing here is generating the software based on our diagram that describes the hardware that we want to create. You can of course write VHDL yourself instead of using the block diagram if you want to have more control over the hardware you create. Now that the VHDL is created, you can click on Generate Bitstream in the Flow Navigator on the left-hand side, located here. Vivado just says that this is the first time the bitstream is being generated for the project, and it needs to run through a couple of different steps before it can make the bitstream. After you click Yes, Vivado will start building the bitstream. Vivado can take anywhere from a few minutes to several hours to build the bitstream depending on how complicated your digital logic is. You can see what step Vivado is on if you look at the top right corner. When it's finished, you'll get a pop-up saying that the bitstream generation has completed. You can hit Cancel. The next step is to export a Xilinx shell archive, or XSA file, from Vivado, which includes the bitstream and other information related to the Vivado project and the PS configuration that you just set up in the block diagram. You can do this by going to File, Export, then Export Hardware. Click Next, then make sure you select Include Bitstream to make sure the bitstream is in the XSA file. If you miss this step, the first stage bootloader will not load your bitstream into the PL. Click Next. Then click Next again if you're okay with the XSA name and where the XSA file will be exported to. Then finally, click Finish. And that's it. We're done with Vivado for this video. But just so you all know, there's a lot more functionality that Vivado can offer. I'm only barely scratching the tip of the iceberg here. If you're interested and want to learn more about Vivado and how to make more complicated digital circuits, I'll provide some useful links below for reference. Now that we have our FPGA bitstream from Vivado, let's generate the first stage bootloader for our hardware. We do this by opening the Vitis tool and either creating a platform project or an application project. I'll be selecting the Create Application project, but let's break down what both of these projects mean and why you would choose one over the other. The platform project reads the information in the XSA file, which is the file you export in Vivado, so that it knows how to set up and configure software for your target hardware platform. The platform project is also the one that's responsible for generating the first stage bootloader for you. On the other hand, an application project or system project will give you an environment where you can easily cross-compile your own application you develop for running on top of the OS that you'll build. Cross-compile meaning you can build a binary from source code for a specific target architecture like ARM instead of for the computer that you're compiling on, which for my case would be an x86-64 Ubuntu machine. So then, if our goal right now is to generate the first stage bootloader, why did I select an application project? Well, it turns out that if you don't already have a platform project set up, selecting an application project will also create a platform project for you. This is because the application project needs to get information from the platform project so that it knows how to build the software for your target platform. Because of that, the setup wizard will walk you through the process in creating both projects. Okay, so we'll be getting our platform project so we can generate the first stage bootloader. Cool, but that still doesn't answer why we want to also set up an application project. Well, one reason is I wanted to show you what it will look like with a Hello World program so that you can get a feel for how to cross-compile your own applications with Vitis. but the main reason is that we'll also eventually be developing our own application for RoboDog on this hardware. So this application project will be setting the stage for when we start doing that in a future video. Let's click Next and provide the setup wizard the hardware XSA file to help generate the platform project. Click Browse and search for the XSA file that you generated in Vivado. You can change the platform name to something else if you want. I changed mine to Zybo Z7-20, then click Next. I made my application project name RoboDog App and changed the target for my application to SMP, which stands for Symmetric Multiprocessing. This will mean that my application will be able to utilize both ARM cores in the dual-core ARM Cortex-A9 processor. After clicking Next, you'll see a bunch of entries here for locating where your various OS components are for the system. I'm just going to leave these blank for now and we'll fill them out later, so click Next for now. The last step in the wizard is what template you want to start out with in the application project. Like I mentioned earlier, let's start with a simple Hello World template so that we can have our application print Hello World in the console when executed on the Zybo processor. Click Finish, and the project will be initialized for you. There will be two projects after clicking Finish. The blue project is the application, and the green project is the platform. If you click on the source folder in the application project, you can see that there's a simple helloworld.c file. If we open up the platform project here, you'll see a folder called Zinc First Stage Bootloader. The folder contains all the source code for building your own first stage bootloader. Make sure that you have the platform project highlighted and select the little hammer icon in the toolbar ribbon. This tells the platform project to build the first stage bootloader. Once the first stage bootloader is built, you'll be able to see the executable ELF file for it in the Zinc FSBL directory located right here. So far so good. We now have our Bitstream using Vivado, and we have our first stage bootloader using Vitis. I don't want this video to get too long, so I think this is a good stopping point for now. In the next video, I'll talk about how you can generate the rest of the OS components, what it all looks like booting everything up on the board, and much, much more. So thank you all for watching, and be on the lookout for the next one.